I wish to show some examples of lateral control. So first of all, we can imagine that there is some sort of GPS data set that contains some sort of dots in space, sort of X and Y coordinates that can be thought of as longitudinal and lateral data points that look something like this. This is a path that we would want our vehicle to take, and from these GPS data points we can construct a path that goes through those points. It would be great if it actually goes through the points, like so, something like this. Okay, now we have a path that we would want our robot to follow. And at the moment, we have our robot right here, and it's heading in this direction. Actually, I'm gonna change the spot. We're gonna put it here, and it's going this way. And right now we have the cross-track error. And what was that error again? It's the closest distance to the path. So this is the cross-track error, as explained in the lecture slides, right here. And if we would use a cross-track error based PID controller, it means that the error that the controller tries to minimize is this cross-track error, the distance between the path and the turtlebot. Now, what is then the output of the controller? The plant is the turtlebot, then the error is the cross-track error, and then the output is the angle where we're trying to, let's not make it so steep, let's make it like so. And so it's the angle between the current heading and like steering to the left. So the bigger this cross-track error, the bigger the steering. So I can demonstrate that. So this is the case 1. Let's say that instead the turtlebot would be this far, still heading that way. This is case 2. Now we have a cross-track error over here that is this big, which results in much larger steering command, like this. Okay, so these are 2 different scenarios. Then if the turtlebot is really far away, let's put the next one over here, number 3, and the cross-track error is this big, then we end up in a situation that the steering command is very steep. And why I want to mention this situation is that then this turtlebot will head this way, will go in time a few steps forward, and let's say that the turtlebot would be here, and then it's facing straight at the path, because the command, this controller made it so that it comes like, you could imagine it going somewhere here, and then we have our turtlebot over here. And now that it's facing straight at the path, what it will lead to is this type of behavior that might stabilize, and then it will go with the path. But this results from the sort of pursuit of trying to get to the point that is right next to the turtlebot. So we can get rid of that by looking ahead into the path and not trying to get to the point that we're right next to, but get a little bit further. So this was cross-track PID, cross-track error-based PID controller, or type of control. And then if in a similar situation we have the path over here, Then we have our turtlebot in, let's say, this spot, and it's looking there at the moment. Well, now the closest distance, let's say, is right here in this spot. Now, rather than looking at this point right next to the turtlebot, we're going to do going to look ahead forward in a distance that is predefined. So this is a constant distance. So we walk in this path the length of look ahead, and then we end up in a point that is in the future in the track, not right next to the turtlebot, but in the future. We're looking ahead. That's where the name stems from, and then we take this line over here. This is denoted as L, and what we want to do now is that we get this angle over here. So the angle between the current heading and where we should be looking at. And this is follow the carrot. This is called follow the carrot algorithm. And now we also need a PID controller, or at least a proportional controller, that controls the steering of the vehicle so that it tries to minimize this this angle over here, this theta. So minimize with PID. So this is the follow the carrot algorithm, and the main difference why it works better is that it's looking ahead to the path, so that it's not causing the same sort of behavior as in here, this oscillating, going back and forth because of over control, sort of oversteering. And continuing on this follow the carrot, we have, I can already write it down, the next one is pure pursuit algorithm, which is very similar to the continuum on the follow the carrot one. First, I will draw this path that we have. We want to get the one we want to get our turtlebot into. Then we have our turtlebot over here, facing that way. Then, as in previous example, we have somewhere we want to get at in the follow the carrot. So this is defined exactly the same way as in follow the carrot, but I don't want to draw all that stuff here because it will make it look confusing when I add more. And then so we have from the turtlebot to this point, that line that was denoted L. And then instead of considering the angle in between the current heading and this line L, we want to follow this type of an arc to that point. And if we take the turtlebot coordinates, I'm going to draw that in color. We want the so the way that this arc is defined, why is it not looking, for example, like this? Is that this arc is defined so that if we go into these turtlebot coordinates and the y-axis of it, so this is the x-axis where it's heading. I could put those in. So x, and then this is y. And so that the center point of this arc, so it's part of a larger circle, like this. The center point of that circle is, it has to be in this part of this y-axis. So now we have the radius of that arc for a circle. And now we can denote that, obviously, since this turtlebot center point is also part of this larger circle, this distance here is just as well the radius of the circle. Now I want to draw some other lines here as well. What color would be least confusing? I think I will pick a new one. Let's make it that color. So, okay, let's make the pen a little bit bigger. Oh, yes. So now we have the, when we're looking at the so if we're looking at the points where the turtlebot is right now, here, and then where we're headed over here, the differences in y and x coordinates are from along this axis, y-axis, and then in the same direction as x. So we have parameters xl. So these are the components of this L, XL and YL. And one more variable that we need is this distance, this very small distance over here, that we will mark here. This is A. And now we can write down three equations. One of them is the triangle that I'm gonna now sort of highlight, then take away, so you just see what I'm talking about. So one of them is this triangle over here. So it has sides are YL, XL, and then the hypotenuse is the large L. Then there is one triangle that consists of the sides A, XL, and then the hypotenuse is this R over here. So we can write those down. We had XL to the power 2 plus YL power 2 equals L to the power of 2. Then we have A to the power of 2 plus XL to the power of 2 equals R to the power of 2. Lastly, we know that R, this radius, consists of A plus YL. So we have A plus YL equals R. So in the lecture slides, these were denoted in a different order. So this is the equation 1, this is equation 2, and this is equation 3. Now, we can start to sort of calculate this forward or open them up. So from using this this equation over here, we get that A equals R minus YL. Then we can use this this information to plug this part to this equation, which turns to R minus YL in the place of A to the power of 2 plus XL to the power of 2 equals R2. Now, if we open this up, we get R2 minus 2 RYL plus YL power of 2 plus XL to the power of 2 equals R. Now we can cross out, since we have in both sides we have R2, we can cross those out like this. And we also know that this part over here, according to this equation here, is just L2. So this is just L2. Now if we do that, we get we get minus 2 R Y L plus L2 equals 0. And turning this, now solving for R, we get R is 2L divided by 2YL. And the curvature of this arc is gamma, and gamma is the inverse of radius. So the steering command at the very end, the result you all been waiting for, if we take this part into account, is gamma is 2YL divided by L to the power of 2. And this is now the steering command that you will give to the turtle bot. I hope this clarified a bit where these equations come from and how they're then derived into this curvature. And I hope that this helps you in the exercise.